Good morning, we are Group 3 and we are going to present our proposed project SCAMOL, Structural Clustering and Modularity Optimization with Label Propagation. Here is the overview for the contents of the presentation. Given time constraints, we will go over the contents and focus particularly on number 4, experiments. We did basic experiments as indicated for the mid-progress discussion guidelines. As a motivation for our project, we came up with these rhetorical questions. How can the hidden structures in vast networks be uncovered? Detecting communities within complex graph is a crucial area of research in recent studies. Could a hybrid approach combining gradient descent, modularity optimization, and LPA methods offer a more comprehensive solution to community detection? Community detection algorithms has evolved over the years and has been very useful in various fields, such as social media, bioinformatics, and more. However, with the rapid increase in data and the advent of the information age, challenges in community detection persist. Some challenges include scalability and complex structures, since now networks have millions or even billions of nodes and edges. For a more technical challenge, parameter sensitivity greatly affects results, and optimal values can be non-trivial. To address these challenges, there is a compelling potential for hybrid methodologies that combine the strengths of each traditional clustering algorithms, aiming to improve the robustness and accuracy of graph analysis. Our proposed contributions include a 2D gradient descent to optimize scan parameters, by setting the loss function to maximize the modularity. And since we had problems with scan results due to the outliers and hubs, we used label propagation after scan to put every outlier and hub to be in exact singular cluster. We reviewed related works, especially the ones provided in the project guidelines, such as SCAN. So SCAN identifies clusters based on the structural similarity, which is a popular method, but it requires parameter tuning for optimal performance. However, there are challenges with SCAN, such as that effectiveness is highly dependent on the choice of epsilon and mu parameters, and that SCAN is non-core node handling for hubs and outliers. Another related work is a modularity optimization. It is intuitive and versatile, which is a clear measure of community structure and also applicable to various network types. And modularity optimization is also scalable since efficient heuristic algorithms enable use on large networks. However, it has also a weakness of resolution limit, which tends to miss smaller communities in large networks. And another related work is label propagation algorithm. It is efficient and scalable. It operates in near linear time, making it highly efficient and suitable for very large networks. And it is also simple, straightforward to implement, and does not require prior knowledge of the number of communities. And it also has weaknesses such as stability issues and quality of communities. And we also did additional research on recent and SOTA research, such as methods for community detection in networks, often employ a combination of machine learning, deep learning, and graph-based algorithms. Some notable and recent papers are graph attention networks, graph transformer networks, graph embedding with self-clustering, semi-supervised classification with graph convolutional networks, and also consensus clustering in complex networks.
Moving on to the third section, which is methodology. Our objective is to design and analyze community detection algorithm that is capable of identifying distinct communities within a network. The algorithm should assign every graph node to exactly one cluster as the result. So, we decided to use SCAN as the base algorithm and to use 2D SDD to find the optimal parameters of SCAN to minimize the modularity of each cluster. And also, we decided to use label propagation to remove outliers and hubs in result. SCAN has two parameters, which are epsilon and mu. Epsilon indicates the similarity threshold that determines the threshold of the similarity of neighbors to make them in the same community, while mu indicates minimum number of neighbors to become a core node of SCAN. The key idea is to automatically determine the optimal mu and epsilon using stochastic gradient descent, which is known as SGD. And since there are two variables to optimize, we use 2G SGD. We carefully made the loss function of SGD with various metrics, including modularity from modularity optimization. Automatic parameter optimizations using gradient descent requires manually setting epsilon and mu so that it can be suboptimal and dataset dependent. Automating this process can enhance the robustness and adaptability of scans. The objective is to automatically determine the optimal values of epsilon and mu using SGD, specifically 2G SGD, due to the two parameters. The process involves iteratively update the epsilon and mu using 2G SGD to minimize a modularity-based loss function. Automating this process enhances the robustness and adaptability of scan. Next is the custom loss function. The challenge is optimization needs a metric that effectively differentiates between good and bad cluster structures. Therefore, there is a need for a tailored loss function to drive improvements in clustering performance. The objective is to formulate a loss function that correlates directly with clustering quality. Therefore, the focus is to utilize modularity to assess and enhance the quality of detected communities. The process involved modularity-based loss function, which it implemented a custom loss function, -3 multiplied by modularity cube, to prioritize a higher modularity scores. The modularity evaluates the strength of community divisions, which higher modularity means better cluster. The cube modularity, on the other hand, function by penalizing suboptimal clusters more severely, steering optimization towards better solution. Hence, it will effect in guided optimization where the loss function helps gradient descent algorithm converge to parameter values that produce high quality clusters and also enhance clustering that leads to improved NMI scores, indicating more accurate and meaningful community detection. The third method is label propagation. The challenge is standard scan may leave hubs and outliers unassigned or poorly integrated into clusters, which affect the overall clustering quality. Therefore, there is a need that a method to effectively incorporate these nodes into existing clusters to improve the comprehensiveness of the clustering. Therefore, the objective is to develop a strategy to assign non-core nodes to the most appropriate clusters based on their connection. Therefore, there is a need to ensure that the clustering process is inclusive of all node types, resulting in a more accurate representation of the network's community structure. The process of label propagation involves implementing a label propagation algorithm to assign labels to non-core nodes. Step 1 is by initializing each non-core node with a unique label, then iteratively update labels by selecting the most common label among a node's neighbor. Then repeat the steps until the labels stabilize, meaning that there is no more changes occur. Each non-core node, which is the hub or outliers, is assigned to the cluster with the most neighbors in common, effectively integrating it into the most relevant community. This will bring positive impact in comprehensive clustering, which ensure that the hubs and outliers are not left out, resulting in clusters that include all nodes. Besides that, it will also enhance community structure, which improve the accuracy and completeness of community detection as reflected in better clustering metrics. This method helps achieve a more realistic representation of the network cluster community structure. The post-experiment method involves new method. This is because suboptimal parameters used for 2D SDT can lead to inaccurate clustering results, which affect the overall performance and reliability of the algorithm. The objective is to achieve a better starting point for optimization, which lead to faster convergence and improved results. This involves selecting initial parameters values that are likely to optimize the clustering process more effectively. By using the knee method, significant inflection points in the evaluation metric are identified and used as initial values for epsilon and mu in 2G SDG. These points represent critical changes in the metric, indicating that optimal parameter values for the clustering algorithm. Next section is the experiments. These figures are the test result of accuracy tests using NMI predicted algorithm. We use initial epsilon of 0.5 and initial mu of 2 with the learning rate of 0.01 for epsilon and 0.1 for mu. The gradient descent was executed for 50 iterations on TC11, and these are the following results that shows clustering accuracy compared to the ground truth. We use NMI for metric, and we can see that MNI increases over iteration. This suggests that the clustering algorithm is improving its ability to accurately identify clusters as the number of iterations increases. The modularity also increases over iterations based on the second graph. Even though NMI doesn't show a consistent trend at the beginning, but after iteration 10, it is consistently increasing. This suggests that the algorithm might have needed some initial iterations to adjust its parameters before achieving significant improvement in the clustering accuracy. While the NMI value is not extremely high, the overall upward trend indicates that the clustering algorithm is performing reasonably well, and the increasing trend is a positive sign that the algorithm is converging towards a better solution. So we concluded that the gradient descent succeeds to find the local minima of parameters. Figure shows the comparison of our SCAMOL method with pure LP method. The graph shows that the SCAMOL method outperforms the pure LP method in all the cases of TC11 using NIM method. The NMI scores for the SCAMOL method are consistently higher than the pure LP method. This indicates that the SCAMOL method is better at clustering the data and finding the underlying structure. Therefore, it can be concluded that this hybrid approach is more effective than the pure LP method because it is able to overcome the limitations of the pure LP method. In subsection 4.3, the effect of implementing the NIM method can be seen from the two graphs. It can be seen that the NIM method helps improve the accuracy of the model. Comparing the NMI scores over iteration for using NIM method and manual starting point, we observe that the model using the NIM method reaches higher accuracy with fewer iterations. This is due to the NIM method finding a better starting point for the parameters. Increasing modularity does not help if the starting points of the parameters is wrong. It can actually hinder performance if the starting point is not optimal. The second test is the scalability test. For scalability test, we use TC2, in which the size of the dataset in TC2 is doubled when the number increases. The running time of the algorithm on these datasets initially triples when the dataset is doubled, but the increasing rate converges to 2 when the dataset is large enough. Hence, we conclude that it shows good scalability to the larger dataset. For our paper, the conclusion includes 3 limitations, which is parameter sensitivity. The performance of each algorithm can be highly sensitive to its respective parameters. Therefore, it is difficult to find a set of optimal parameters that work together. Next is overfitting to noise, which might happen when combining multiple methods, or the algorithm might capture noise or insignificant patterns in the network instead of true community structures. Generalization capability can also occur when specific datasets are used. This can be achieved by using diverse training data, robust evaluation metrics, and ensure that the algorithm does not become too specialized for a single dataset. The first feature improvement for our dataset is enhanced loss function. Current reliance on modularity might overlook the other aspects of clustering quality, including metrics like conductance and cut ratio can provide a more comprehensive evaluation. The goal is to improve the clustering quality by considering additional evaluation metrics. This ensures that the detected communities are not only well separated but also exhibit desirable structural properties, improving the utility of the clustering results for domain experts. Another improvement is the hyperparameter tuning. The learning rate directly affects the convergence speed and stability of gradient descent. Fine-tuning these and other parameters can significantly improve performance. The aim is to find optimal settings in order to enhance the performance and stability of the optimization process. This leads to a stable and precise optimization, resulting in high-quality clusters that accurately reflect the network structure. The last section is the reference. And with that, we concluded our paper on SCAMOL method. Thank you.